Hello, can you hear? Yeah? So done now with chapter 7 in your tutorial. Who's still working on it? Who's done? Who's done? Which class is done? One more class? Any questions? Chapter 7? Chapter 7 is associated with chapter 8, obviously. I've already touched chapter 8 here and there. I think you have written the TS diagram without realizing that you wrote the TS diagram one day. Yeah? S is entropy. You wrote it one day. You wrote a rectangle one day. You can look in your book. Okay, the way you need to get into chapter 8 is you have to do a small recap with chapter 7. One more time. You have to do the Carnot engine. Because the whole concept of entropy came about from a very macroscopic context. It came from a macroscopic context. Obviously today we use it in molecules and atoms and electrons, and we use it in a microscopic and nanoscopic context, but the funny part is it came with a very macroscopic context. So the point was, I kept saying heat is getting rejected, discarded. Remember, in your heat engine, it came from that. So people always want to see how much work you can get out of something. But then you also look at the other side of the coin as to why you are not able to get it. So that digging into why you are not able to get it led to this wonderful thing, that you will not get it. So that discarding is what Clausius's big discovery is. How many years ago? Nearly 160 years ago. He was playing around with the Carnot engine, basically. That's all. So that has turned into one huge microscopic thermodynamics in material science. So let me start off like that. So what I want you to do is, one more time recap, last part of your 7th chapter you recap. Go back to your Carnot. Again, like a broken record player, you like to start from evaporation, that is isothermal expansion. Isothermal expansion. So your internal energy is 0. So Q is equal to work. You can assume your ideal gas thing. And then what do you get? You get, it's a hot location. It's isothermal evaporation. It's a hot location. So you get RTH ln V2 by V1. Can you look at it? Then what happens? Next step, you use that temperature and pressure to do work. Turbine. You got an adiabatic expansion going on there. So Q is 0, and then you have U equals W. Change in U. Change in U equals change in W. So du is CV dt. And then you have your usual RT. So you divide by T, and then you will get an integral CV dt by dt is equal to ln. What do you get? Ln V3 by V2, or ln V3 by V2. So you keep going on and on, back compression cycles. Then you have CVs, right, in your two adiabatic conditions, correct? Adiabatic expansion and adiabatic contraction, you have CV terms. So you can equate the CV terms. In one case, the integral goes from TH to TL, and in another case, it goes from TL to TH. So you equate that, and you will get one volume equation. Can you write it? What is the volume equation you get? I will start from there. So what is the volume equation you get? I think you get something like V2 by V1 is equal to V3 by V4. Is that correct? Yes? Yes? Open your book, man. Got it? You have to do a manipulation. If you equate both the adiabatic terms, adiabatic expansion and adiabatic contraction, you will get V2 divided by V1 is equal to V3 by V4. Okay. This is just a ratio of volumes, nothing significant here. But now you go back to your isothermal terms. You go back to your isothermal terms. You put your QH and you put your QL. And then take the ratio of QH and QL. Tell me what happens by using this volume ratio. Do it. Your QH is what? RTH ln V2 by V1. QL is RTL ln V3 by V4. So V3 by V4 gone, R gone. What do you get? QH by QL is equal to TH by TL. Got it? Write it. Write it. So first what you did, you made a nice Carnot cycle. You wrote the equations for the Carnot cycle. Then you equated the adiabatic terms. When you equated the adiabatic terms, you got some ratio for volume. Then you went back to your isothermal terms and you took the ratio of the isothermal expansion and isothermal contraction. So what you got is big QH by QL, because all the RR got cancelled, the logarithmic volume ratios got cancelled. You got so now you just manipulate this, again you write it as QH divided by TH is equal to QL by TL. That is basically what Clausius did. That was his first step. Started with a very basic Carnot engine. He measured these. There is nothing, there is no mathematics here. He measured it. Experimentally measured it. And then he figured, like he's scratching his head, the ratios of the heat is the same as the ratios of the temperatures. Temperatures are in Kelvin. Temperatures are in Kelvin. Don't go and write Celsius in the exam. So what is his first big finding? Is he found this constant. Wonderful. This is a huge discovery. This is. You see, both are macroscopic quantities. Q is a huge macroscopic quantity. There is no microscopic, there is no molecules here. And temperature is a macroscopic quantity. This is his big finding. And this is for a reversible process. I think I've already gone through reversible and irreversible. Can you write it? This he did for reversible process. So what is a reversible process? 2 marks. I go slow, small amounts, and I change slowly. Get it? Every step you create equilibrium. You change a little, you wait for everything to settle down on both sides, you create an equilibrium. Then you again change a little bit. Then again you wait. Then again you change a little bit. Then again you wait. Slow process. Very, very slow. Write it, man. Lecture is for conceptual things only. Slow and gradual reversible process. Every step you will make one equilibrium, quasi-equilibrium step. Like a stalemate. You will create a stalemate. Then you will change a little bit more. Overcome that. Go to the next stage. Again wait for it to block. Create a stalemate. Again you go to the next step. Step by step. And then he decided, let me have some fun and do an irreversible process. I think basically he went really fast. What do you think must have happened? What do you think must have? Now it's back, we are back to question and answer session. This is for reversible. He went slow, and gradual, and he got this REV, reversible. But you know how the brain works. When you do one thing, you want to do another thing. So he decided, let me spoil the slow and gradual and go really fast. What do you think would have happened? Yes. So you have to go back to this schematic only. I have a hot location, I'm supplying heat, correct? Then what do? I get some work, and then I come back here, I come to the cold location and I reject heat. Yes? Got it? That is the concept you have to use. Now he went in a very irreversible fashion. What could have happened? So you have to think, will the rejection be more or will the rejection be less? Do you get more work or do you get less work? So that was his basic idea, to see how I can get more work, but also to think why I am not getting that much work all the time. Louder. When he was doing a REV or a irreversible? Okay. Why you say that? I know, but rejection is a consequence of not doing that much work. It's not the other way around. Correct? The work step comes before the rejection. Am I right? You're on the right track. So don't focus on the rejection. Why he must have got less work? That is why he might have got more rejection. Possible. Possible. But why he got less work? Why W reversible is greater than W irreversible? Why? 2 marks question. So I've already told you what a reversible process is. Small amount, slowly. So for work to be done, do you need to give, is there a lot of kinetics involved? Yes or no? Huh? Obviously yes. You need everybody to unify and work towards a purpose. Yes? And there is going to be a lot of diffusional scenarios there. Things have to move. Volume is changing, correct? PDV. Work. Correct. PDV. If you hit a tennis ball slowly, gradually with a nice, beautiful loop, will you make wonderful contact? Or if you flail your hands and just do that, will you make a wonderful contact? Which one does the coach teach you? Just slap at the ball and flail your hand, or make a nice loop, keep your body balanced, maintain equilibrium, and when your contact, make good balanced contact. What does the coach teach you? Former or latter? Which one? Balanced or slap at the ball? What happens if you slap at the ball? Nothing. Everything is friction, that's all. Yeah? It'll just fly all over. You won't even make proper, you can even whiff at the ball. You'll whiff at the air. Yes? You do not orient the ball in the direction that you want to smack it. Correct? So you have to go really, really slow. As much as possible when you're doing work, you have to keep it as a reversible, equilibrium, balanced process. If you just do it try to do it very fast, you lose the balance. What balance you lose? From the initial state to the next state. And if you lose that balance, slowly you lose orientation. Slowly you lose orientation, the work will increase or decrease? Decrease. Tremendously it will start decreasing. You're losing orientation. That purpose is not even going that way. Got it? Slowly you start to lose. So then what do? Everything starts to get discarded. Then you will get heat being rejected. Yes? So now you tell me, your friend already went in the right direction. When Carnot did the irreversible, what happened to the fraction? So obviously it's not equal. So then what could it be? So QL will be very high. Yes? Correct. Your rejection is very high. Wake up everybody, QL is very high, correct? So what will happen to the fraction? QH by TH will be greater than QL by TL or less than QL by TL. What did Carnot come up with? Less than. Can you write it? That is your big Clausius inequality. So when you have a reversible process, the two fractions are equal. When you have an irreversible process, QH by TH minus QL by TL is less than 0. Less than 0. So reversible, it is equal to 0. Write it, man. Reversible is equal to 0. Irreversible is less than 0. So this is your Clausius inequality. So if there is multiple processes, how do you write this? If it's multiple processes, how do you write it? You put a summation, because it's a multiple, it's a cyclic process. If you want to write it in integral, you can write it in integral. If you want to write it as summation, you can write it as summation. Can you write it in integral? This is a reversible process. Correct? I wrote it as a cyclic integral here. Yes. Can you write that for irreversible process, cyclic integral? Dou Q, you know why I'm writing dou, right? It's a path function. So dou Q by T less than 0 is irreversible. Put both together. So integral dou Q by T is less than or equal to 0. This is the famous Clausius inequality. So why we write a cyclic process is because we may not have only one process. We can have 100 appliances. So it's a continuous process. Clear? This is an integral for cyclic. Cyclic. See where you ended up from a simple but a wonderful observation, a macroscopic observation. So you have to keep harping on the rejection, got it? Rejection is the key. So now can you understand how Kelvin Planck can never happen? Or Kelvin Planck statement is the truth. Why? All the heat that is given cannot be oriented and made into work because your entropy will decrease. It cannot decrease. You need to have rejection. Yes? That is what Clausius found. That you need to have rejection. You cannot have a perfect, convert all the Q to work. Not going to happen. That's a Kelvin Planck statement. Yes? You can easily see it now. That will not happen. Can you now see the Clausius statement? Will heat automatically go from cold to hot? In this only you should see. In this itself you should be able to see. Conceptually, you know, Kelvin Planck is right. All the heat cannot be transferred to work. Entropy will decrease of the universe, of both the surroundings and the system will decrease. Not going to happen. That will not happen. Now can you identify the Clausius statement in this? That heat cannot spontaneously go from cold to hot. Correct. Correct. If that happens, then QL by TL will become greater than QH by TH. That's not going to happen. It's like as though the entropy decreased. This equality, this won't hold. If you go and do convert from cold location, you go to hot location without doing any work. That is what that is, right? You cannot remove heat from cold location to hot location without doing work. You have to do work. You have to compress it. Yes? Spontaneously, you cannot take heat out from cold to hot. From hot to cold you can, not from cold to hot. So when you go from cold to hot, what happens? Here, what happens? Who loses entropy? Cold junction or the hot junction? He just said the equation. You have to prod him and ask him a few more questions. Who loses the entropy? It's going from cold to hot. Who loses the entropy? Cold. Who gains the entropy? But hot is already hot. How much of a gain will happen? Not much. Hot is already hot. Who lost a lot? Cold. So when you do the arithmetic, you will get an overall decrease in entropy. Not going to happen. Got it? Hot never gains much. Hot is already hot. The temperature that you have in the denominator is an indication that you are already quite active and disordered and your energy states are all occupied because you are hot. Yes? You are hot. Hot means all the energy states are occupied, even the higher energy states, not just the ground state. So if it's already occupied and if somebody gives you Q, how much more will you rearrange? By a lot or by less? Very less. You're already occupied all the energy states. Got it? So it's like giving money to the rich guy. See, again finance came in. I don't know, man. Finance always comes in. You know how that works. Money to the rich guy, money to the poor guy. That's it. Where does the activity change more? Poor guy or the rich guy? You start to make his life miserable now. Just kidding. Entropy is not a miserable thing, it's good. You have no control over it, neither do I, neither does anybody. Give me another example for the same thing. I gave you the rich guy, poor guy example. Give me another example. I'll give you 500,000. Make it million points. Give me another example, just like that. Analogy. There's time for some checking on the analogy skills of students. Okay. Good. That will work. But that is a little bit of a mass dispersion. It's both mass and energy dispersion. The water also will occupy different states. The salt also will occupy different states because of physical mixing. Correct? There is a dispersion of both mass and energy. Good. That will work. One more example. Sneezing in a crowded place in the market and sneezing in a quiet library. Where does the change in entropy happen more? Library. What are we talking about? Dispersion of sound. Dispersion of sound. they will occupy more energy states and they will mix much better. They will disperse better. They will disperse better. Yes? So guess what Clausius did? He has to give a name for it. He has to give a name for this. So he wrote a paper in 1865 and he used a Greek word called as transformations. So he wrote a Greek word for transformations, entropy. I'm sure he's thinking dispersion only. He wrote it as transformation. Entropy. It's a 1865 paper. So he coined this ratio as entropy. So how do you write it? Because you're already writing a state function there, dou Q. So it's a change in entropy. Delta S, right? What's the units? Right from there you can tell the units. Huh? What's the unit? Joules per degree Kelvin. But it is also an extensive property. It depends on how many molecules are there, how much mass is there. So joules per gram degree Kelvin. And you can write it either in grams or you can write it in moles. Obviously you know how to change it. You need the molecular weight of the material. Yes? Okay. You can either write it as joules per degree mole Kelvin or joules per gram degree Kelvin. It's a state function just like your U, internal energy. But heat and work is path function. So this is where it got coined, entropy, S, the big S. So the first law will tell you what is the conservation and the constancy of energy, correct? Yes, conservation. What does the second law tell you? What is the dispersion of the energy? Can you write it in your nice own beautiful words? First law tells you conservation or conversion. Obviously, conservation happens because of conversion. One form can go to another form. Write it, man. You write it. Only if you write there's magic. Then you can ask me questions. If you hear me, it's no use. I'm no good. If you hear to me, it's of no use. Make it run in your mind. You write it and ask me some questions. First law very clearly tells you only about conservation. That you cannot build or break anything. It's constant. We are talking of the universe. So don't forget, I'm talking of universe, which includes both the system and the surroundings. What does the second law tell you? It tells you the dispersion of the energy. And a process is spontaneous only if dispersion continues to increase. So Clausius wrote in that paper with a big generalized statement saying that the entropy of the universe will reach a maximum. Long time ago he wrote this. Long time ago. That it will continue to go in the increased direction. Got it? So there is no conservation of entropy now. If I ask just for fun, 1 mark question, trick question, don't write entropy is conserved, yeah? Okay. I might like to ask such kind of questions, as you know, since we are spending time on it. Can energy be conserved? Okay. How the energy is distributed, can it be conserved? Huh? I asked the same question. I answered the question and asked the question. Can energy be conserved? Obvious. Can the distribution of how the energy is distributed, can that be conserved? No. It can go to various distribution levels, and it will always go find where you have the highest number of ways of distribution. So why you say yes for it now? I just asked the same thing in another way. Yeah? Can the distribution of energy be conserved? No, you cannot. It might remain the same, but it will increase. It might remain the same, or it will increase. It will increase. It will increase. So all of you say these things like disorder. I don't know, some of you guys even go as far as using words like chaos and all that. Calm down, now. Don't go with chaos and all that. So right now we are using words like dispersion and disorder and all that. But what is it exactly? He gave a good example of salt in water, sugar in water. So what is happening is that you are exploring more energy states. That is what you are doing. The total energy remains the same. Got it? The total energy will not change. It's just how you distribute them will change. And it will always go towards a maximum distribution point. It looks for ways to distribute in more number of ways. And the most number of ways is the most probable state. So what am I talking about? Dice. Which number most probably will fall? When I drop 2 dice, which number will most probably fall? 2 dice, which number when you add them will most probably appear? Simple question. 2, 3, 4, 5, 6, 7, 12, 10, which one? Which one will most probably appear? 7. Because you can get 7 in more number of ways. Yes? What are the ways? 6, 1, 1, 6, 2, 5, 5, 2, 3, 4, 4, 3. No other number can you get it like this. So obviously that will be the most probable. Get it? Understand? You can play with cards also. You can do the same thing with cards. You will always get the most probable state. And what is that most probable? Which has the highest number of ways that you can get that state. Get it? Common sense, right? There's more number of ways you can reach the same destination. That's the most probable destination everybody will reach. 7. If you don't believe me, nothing. Take 2 dice. Get one friend to count about 1,000 times that you drop the dice. And in that 1,000 times, you write how many times you got 7. You put all the numbers. You do 1,000 trials, 1,000 sampling. Have some fun, man. Come on. Otherwise, I'll give it as a project. Just drop the dice and come back and correctly tell me how many times you got 7 out of those 1,000 times. If you get more number of 12s, then we have changed our history. Come on, it's a fun thing. You might, who knows, it might happen. You might get more number of 2s, 1, 1. Every time you put 1, 1. So a little bit lay off the word disorder and dispersion. What it is it goes to different energy states. The total energy remains the same, it just gets distributed more number of ways. So 5, 2 is one kind of a microstate, got it? 4, 3 is another kind of a microstate. 6, 1 is another kind of a microstate, yes? So why is 7 the most probable state? Because you have different ways of achieving that. So that is the most probable. That Clausius did not do, that our friend Boltzmann took it up in the 20th century and he straight went into statistical probability. Because our friend told dispersion, he took the dispersion into combinations. Combinations into probability. Wonderful, right? Because you cannot have more number of dispersions without invoking statistical concepts. Yes? Because now if you bring it to molecules and atoms, you have Avogadro number of molecules. So that is how macroscopic went straight into microscopic. So now a simple question. At a low temperature, two materials have two different heat capacities. Material A, CPA, is lower than CPB. What would you comment on it? I purposefully put it as lower temperature, just for fun. CPA is lower than CPB. What is your interpretation? What are you visualizing about that material? Already went through heat capacity. Heat capacity is nothing but distribution and dispersion. So I'm answering the question. I think if I open my mouth some more, no use. Yes. Who disperses more? CPB. Yeah? Yes? So what does that tell you about that material? Can it occupy and have come up with more distribution of energy states? Yes? Yes. So is it more mobile or is it frozen? Obviously it's mobile. Yes? It can make a lot of combinations. You need mobility to make combinations. Got it? For it to go to different energy states and combine. Now the guy who is sitting at the bottom needs to go up and occupy a little bit. He's got to move. You cannot simply go to a high energy state by being stationary. Yes? So for you to make combos, you have to shuffle the cards. You need mobility. Yes? You have to mobilize. So whichever material has high mobility will have high entropy. And that in turn will have more higher heat capacity. Word of caution, that has got nothing to do with that ability of that material to do work. Clear? Don't confuse work and bring it and dump it into entropy. Yes? Entropy is sort of like, I'm going to go ahead and say it, like an antithesis for work. Do you understand? It is not work. It is the other way around. It will distribute and distribute and distribute and come up with combinations. It will not orient and give you one unified purpose and work. Clear? It is not work. It will distribute. A high heat capacity material will hold a lot of heat and disperse it really well and distribute it. But will it expand and do work and supply that heat? That you don't know. Will it have higher thermal conductivity and conduct and do the work? That you don't know. Conduction is work. Expansion is work. But simply holding the heat is not work. It's dispersion inside the material. Yes? So now, in another way, will a crystalline ordered material have high heat capacity or a slightly defective material have a higher heat capacity? Obviously, defective material. If you are ordered and all nicely bound, you cannot disperse, you cannot move. Yes? You cannot move without doing work. Then if you do work, then it will become work. It is not dispersion. So can you come up with some more examples like this by yourself? Yes? It is just pure dispersion. So some people will say dissipation. It's not dissipation. It's dispersion. So it's making combinations with energy states, various energy states. So if a battery has a high heat capacity, what is it doing? Sorry, if it has a high electrical capacity, obviously everybody wants high capacitance in a battery, yes? So what is it doing? Is it dispersing, or is it dissipating, or is it doing work, or is it reflecting or scattering or refracting or deforming or conducting, or I don't know, whatever else you want to add? What is it doing? It's dispersing what? Electrical energy. It's dispersing electrical energy. Yes? That is a battery, high capacitance battery. So it has to hold a lot, it has to disperse a lot. For that it has to make a lot of combos. Anything else? Shoot off questions. I think I've come and defined entropy. That's what I wanted to do today. Basically define entropy. Anything else you want to ask me? Any other question? Entropy is a state function. It doesn't care whether you go which path. It's a state function. So you use the same rule of mixtures also for entropy, just like your internal energy. Got it? Rule of mixtures. You have used it for the same. Don't blink at me. Rule of mixtures. When you are in the two phase inside the diagram. Get it? For pure substances. Entropy of pure substances, when the phase is transitioning from solid to liquid or liquid to gas, you have to use the rule of mixtures. So where are all the entropy values there in your tables? Is it there? Sure. How you know? Okay, you have gone and looked at it. Okay. So you have specific volumes, then you have internal energies, then you take care of the work done and you have enthalpies, and now you have the dispersion, which is the second law, which is actually the most important law. Because without dispersion, the process will not happen spontaneously. First law only told you that it is conserved and you can convert, but it did not tell you whether it will happen spontaneously or not. So two more questions. So now do you understand what's the significance of T in the denominator? Huh? What is the significance? If I sneeze in the library and sneeze in the, yeah? Got it? So without Clausius doing anything, it got normalized by temperature from his Carnot cycle calculations. That's the funny part. It came out so well. It came out so well that it took care of everything. If you had simply written dou Q, would it make sense? Huh? No, it won't make sense, because you have to know at which temperature the dispersion is happening. At a higher temperature, the change in the dispersion will always be less. But at a colder temperature, it will always be more. And the denominator already took care of that. That's the beauty of his fraction. Take a look at the denominator. It's got all the physical meaning there. Simply writing dou Q won't make sense. Correct? So if I give you bookshelves with 20 stacks, like cubicles or partitions or whatever you want to call it, stacks, what are the books there? I will start your books are molecules, correct? Yes? Books are molecules. I'm arranging the molecules now. What are those stacks that I've given you? Huh? No, when the book occupies that, that becomes energy state. But what is the overall number of stacks? Who controls that? Who controls that? Very good. Very good. You said energy, that when the book occupies which particular stack, then it becomes the energy state of that stack. But how do you know that many energy states are there? Who gave it? The carpenter. Yes? So what is the carpenter? Is the temperature. Yes? Carpenter is the temperature. He tells you how many stacks are there and how many shelves are there. How many books are there is the number of molecules that you have. The arrangement that you make is depending on how you arrange it. Correct? And each stack that the book occupies will tell its energy state that it occupies. Correct? You can expand your mind a lot more. So the denominator took care of how much is available already before you make the arrangements. Yes? What is the significance of the numerator? Again, million points. What's the significance of the numerator? Why work term was not put? Obviously work term did not come about. Work done is organized. Heat is disorganized. Random motion. See, it took care of everything. Get it? Heat controls dispersion and random motions. Work does unified and organized motion. So it does not make sense for you to have a work term when you're talking about dispersion. Clear? Yes? Significant. It takes care of both. Everything. And this is for a reversible process. This is for a reversible process. So from now on, start writing REV in the subscript. It's good for you because in your numericals you may have to be careful. They will say an adiabatic process, then they will say adiabatic reversible process. Careful, yes? Exactly. If I say both, adiabatic and reversible process. It becomes isentropic process. Isentropic means delta S is 0. It won't change. S won't change from state 2 to state 1. So let's little bit have some little more fun and put all this little more organized. I'll ask you some more questions next class and then maybe move into, I don't know, what else is there? Entropy. Entropy of ideal gas. Catch you guys.